Copper is an excellent conductor. So if a wire becomes thicker, shouldn't all of that extra metal carry more current? At low frequencies, the answer is yes. But at RF frequencies, something surprising happens. Current begins to crowd near the surface of the conductor, leaving much of the interior barely used. This phenomenon is known as the skin effect. In circuit theory, we often assume that current flows uniformly throughout the entire cross-sectional area of a conductor. This assumption works well for DC and low-frequency circuits, where electrons are distributed relatively evenly across the wire. However, RF engineers discovered that conductors behave differently at high frequencies. As frequency increases, the current distribution becomes increasingly uneven. Instead of utilizing the entire conductor, the current concentrates near the outer surface. This behavior creates an important engineering challenge. If most of the conductor interior carries little current, the effective conducting area becomes smaller. This increases resistance and power loss, making conductor behavior frequency-dependent. Understanding this effect is essential in RF and microwave engineering. Skin effect is the tendency of alternating current to concentrate near the surface of a conductor as frequency increases. The phenomenon occurs because changing currents generate changing magnetic fields. These magnetic fields induce additional electric fields inside the conductor, which oppose the flow of current in the interior regions. As a result, current naturally shifts toward the outer surface. The depth at which most of the current flows is called the skin depth. At low frequencies, the skin depth is relatively large, and current occupies most of the conductor. At high frequencies, the skin depth becomes very small, forcing current into a thin layer near the surface. Intuitively, imagine a highway with many available lanes. Under normal conditions, traffic uses the entire width of the road. Now imagine barriers gradually closing the inner lanes, forcing vehicles toward the edges. The usable area decreases, even though the physical road remains the same. Physically, consider a copper wire carrying a DC current. The current distribution is nearly uniform throughout the conductor. Now replace the DC source with a high-frequency RF signal. The rapidly changing magnetic fields generated by the current create opposing effects inside the conductor, pushing current toward the surface. Mathematically, skin depth decreases as frequency increases. This means that doubling or tripling frequency reduces the depth available for current flow. At microwave frequencies, only a very thin outer layer of the conductor may carry the majority of the current. Skin effect is one of the major sources of conductor loss in RF systems. Since the effective conducting area decreases with frequency, the AC resistance of a conductor becomes larger than its DC resistance. This effect influences transmission lines, coaxial cables, PCB traces, waveguides, antennas, filters, and RF connectors. Engineers often use highly conductive surface materials such as silver plating because the surface carries most of the RF current. At higher frequencies, conductor geometry becomes extremely important. Hollow waveguides, plated surfaces, and specialized RF structures are practical because current naturally flows near the conductor surface anyway. Understanding skin effect allows engineers to optimize performance while reducing unnecessary material usage. Skin effect demonstrates that high-frequency circuits cannot always be analyzed using low-frequency intuition. As frequency increases, electromagnetic field behavior becomes increasingly important in determining circuit performance. A common misconception is that making a conductor infinitely thicker will always reduce RF losses. In reality, once the conductor thickness greatly exceeds the skin depth, adding more material provides little benefit because most of the current remains near the surface. Skin effect is only one consequence of high-frequency electromagnetic behavior. Conductors themselves begin to exhibit characteristics very different from those seen in ordinary circuits. In the next lesson, we will explore conductors at high frequency and discover how RF signals interact with conductive materials in practical systems. In this lesson, we learned that skin effect causes high-frequency currents to concentrate near the surface of a conductor rather than flowing uniformly throughout its cross-section. We also saw how skin effect increases conductor losses and influences the design of transmission lines, antennas, waveguides, and RF components. In the next lesson, we will explore conductors at high frequency and discover how conductive materials behave when electromagnetic fields operate at RF and microwave frequencies. If you found this useful, like the video, subscribe, and follow for the next lesson.